Hello, welcome to the next in the series of technical overviews of magnetic separation equipment manufactured by Buntings in Redditch. Today we're going to look at the eddy current separator and its application in different industries. My name is Neil Rowson. I'm the laboratory manager at Buntings in Redditch and also Emeritus Professor of Minerals Engineering at the University of Birmingham. So I envisage the talk will last probably 25 to 30 minutes and hopefully it's going to be of interest to you. So a bit of background on the eddy current separator. They are widely used in the recycling industry on numerous types of application for the last 40 or 50 years or so. They're used to recover conductive materials from non-conductive materials in waste streams, so for example plastic from aluminium. Different designs are on the market which enable separation down to a particle size in the range of 2 to 3 millimeters in size. Buntings in Redditch manufacture quite a wide range of eddy current units for different applications and different price points. Including both concentric and eccentric design types, which have advantages and disadvantages in different applications. So we're looking here at a machine that will remove conductive materials from non-conductive materials at quite a coarse size range. There are many applications for eddy current separators in the waste processing industry. And a few examples are in the slide here. We're looking at applications like the removal of non-ferrous metals, copper and aluminium, from auto shredder residue, ASR, which is a product from the scrap recycling of petrol and diesel cars. We're looking at aluminium beverage can processing from household waste, which was probably the initial application for this type of unit. Removal of conductive materials like aluminium and stainless steel from crushed glass cullet. Recycling of waste, these are shredded secondary goods from households, things like fridges and electrical products. Again, we're looking at the removal of copper and aluminium and sometimes more exotic things like gold, etc. from these products. Removal of aluminium components from shredded and recycled UPVC windows. Again, we're seeing a lot more of these being recycled nowadays, and it's a great way of recovering the aluminium component and getting a clean plastic product as well, which can be recycled and reused, which of course is very important nowadays. So a look at the design of an eddy current separator. They all follow the same basic principle, but there are different design quirks according to individual manufacturer's preference. So what we start with, and the working part of the eddy current, is really a rotor which contains rare earth magnetic materials. These are neodymium boron iron magnets, and they are set in a north-south, here we go, the north pole, south pole, for example, configuration around. So we're going north, south, north, south, north, south, all around the outside of this this rotor. It's a fast spinning rotor, so it will spin in the region of probably 2,000 to 3,000 RPM, again depending on the application and also the manufacturer's preference. So a fast spinning rotor, and it's that change of north to south pole when a conductor is passed over the surface of it that creates the eddy current force that forces the conductors from the rotor. So it's merely the eddy current separator is merely a method of inducing an eddy current force in a conductive material. Before 40 years ago, in the advent of neodymium boron iron permanent magnets, which are very strong, this would have been done by changing electrical current in something like a linear motor for a railway or something like that. So we place our fast moving internal rotor into a outside pulley here, which will house it. And the concept now is we have a machine that will self-clean and remove material. So we basically feed material onto our usually vibratory feeders, fed can be fed from by different methods, but the ideal method is vibratory feeder fed. So we get a nice monolayer of conductive and non-conductive material onto our feeder belt, which is normally a robust rubber belt, because these materials can be quite abrasive and sometimes quite heavy. We can go up to quite large particle size ranges on this material. So my yellow particles are non-conductive materials like a plastic or stone or glass, and that they just fall off the belt via their own centrifugal force. Our conductive materials come into the influence of the rotating eddy current rotor, which is really an area from here to about here inside in area for this particular type of eddy current design, which is a eccentric design, which means that the actual rotor doesn't take up the whole of the inner shell. So as our material falls into this area here, our conductors are influenced by the changing field of magnetic field. That imparts a force onto the conductive particle and throws it physically from the roll surface in that direction by a combination of Lenz's law and Faraday's law. So materials thrown off this way, non-conductors thrown off this way. So for example, copper here, plastic here. Now when we're separating a process, then we can control the separation based upon a number of factors. First of all, the feed rate that we're putting onto the machine and the belt speed, the rotational speed of the rotor here. The higher the rotor speed, in theory, the more force we're going to put on a particle and the further it's going to be thrown. So really it's the difference between the belt speed feeding the material on and the speed of the rotor that will define how far a set particle size particle is thrown in the eddy current separator. So these are both controllable on the machine independently, so we can optimize separation. The next thing to control would be the splitter plate position here, where I can cut it in and separate. If I have near particles of non-liberated particles, I can cut this in and take a fraction further into the conductive stream or further into the non-conductive stream, depending on the application and depending on the nature of the particles that are being processed. We have an internal rotor going very fast, 3000 RPM, giving us the alternating magnetic field, which creates the eddy current force on our conductors. And we have an outer rotor here, which is a means of presenting the material into and out of the eddy current feed. On top of that, we will have a belt, which is a feed mechanism to ensure an even monolayer of settled particles before they go into the region of separation on the magnetic separator. Again, it's very counterproductive to have particles that are bouncing or quite ballistic in nature as they go into the field, because that means you're not going to get a settled separation and can get misplaced particles. Sometimes we can have a belt cleaner system on here if the client wishes to clean the belt prior to coming back into the feed area again. So that's the basic operating principle of a permanent magnetic eddy current separator, and most of the other things we're going to talk about in this presentation are variabilities in design depending on the application and the amount of money that a client is prepared to pay for this sort of unit. So often these eddy current separators are put in series with a magnetic separator to remove any magnetic particles prior to processing over the eddy current. So if we have some mild steel, for example, in our shredded scrap feed, then first of all, we don't really want to feed it onto the eddy current separator, because this is also a magnet as well as an eddy current separator. And if we have large particles, they may stick on the high intensity field and damage the belt. They also might also build up in the area. If it's very fine dust, then it might build up in this area here, again causing some belt wear and processing problems. So in an ideal world, we do like to put our feed over either a barium ferrite ceramic magnetic drum, or in some cases a rare earth drum magnet, to remove any ferrous material separately before I send my conductive particles and non-conductive particles onto the eddy current separator. That will maximize separation efficiency, it will maximize capacity for the unit, and also ensure good belt life and good operational lifetime for the product. Let's talk a bit about rotor design. Here we can see how a rotor is put together. This is the front rotor for the eddy current separator. We tend to have a magnetic carrier here, which will be some shaft, and the magnets are keyed into that shaft, as I said before, in a north-south configuration across the width of the shaft. So there's bands of these magnets around the shaft. So they are keyed into the shaft itself and project out the field onto the surface of the belt, which will go over the top of this. Now, depending on the magnet depth and the magnet width will determine how far that magnetic field is kicked out onto the belt surface and how many poles that the particle will see as it passes over. So again, the more poles that the particle sees up to a maximum, then will define how far the particle is thrown or how small a particle we can capture on the eddy current separator. So in theory, the stronger the magnet and the more poles, the better. But the downside of that is that, of course, that's more cost, and sometimes we don't need that level of performance. So we will make separating rotor designs that contain less poles and less magnetic material for easier applications. So north-south, keyed all the way around the surface. Obviously, because this roll is spinning at 2,000 to 3,000 RPM, then these have to be fixed very carefully. And what also happens is outside, once the design and the fixing of the magnets is complete, we will put a non-metallic shell outside this magnet configuration, which is also to help retain the magnets in their position. This tends to be sort of high wear carbon fiber design. So once that's in place around the side of the magnet, then the magnetic shaft itself is sent for balancing to ensure that that it doesn't flex, or it's stable, and the weight distribution across the whole width of these units, which can be very wide, well over 1 meter in width, sometimes up to 2 meters in width for some applications. So it's essential that they are balanced and the weight distribution is even to stop any flexing during operation over the lifetime of the So here we can see that a section through the magnetic pulley on the eddy current, and here we have a row of, in this case, north magnetic magnets on the surface here, and they're kicking their magnetic field out and influencing conductors as they come over and kicking them off. And our non-conductors are not affected by this change in eddy current. They're not magnetic, and they just fall off by their own centrifugal force. Here we see the splitter plate in position. So we have a band of north across here, then we'll have a band of south, north, south. And this is spinning very, very fast, 2,000 to 3,000 RPM. This is just a close-up of the front pulley system, belt drive pulley here, and the bearing system here. We have an internal rotor and the external carbon fiber shell here on that pulley, and then we have our belt system here, which is a hard wearing rubber type belt with guides here to keep material in the influence of the eddy current field. As I said, these can be very wide in nature and are sent for balancing over a period of time. So we might, in a typical operation, we might have a belt speed that's relatively low going across the separator, but our internal magnetic pulley system is spinning at 2,000 to 3,000 RPM. So it's quite a complex arrangement here to ensure that it doesn't overheat and it gives you a good lifetime for the product. And some of these units have been running for 30, 40 years with just routine maintenance. So there are two basic designs of eddy current separator. They're concentric magnetic rotors and eccentric magnetic rotors. And they are both good for certain applications. One is not better than the other. It's merely that some suit a type of application better than another, and it gives the client a choice and some sort of choice in choosing something for an application, basically. So if we look at an eccentric design of rotor, an eccentric design, the key thing about that is it is the actual internal magnetic structure, which is here, does not go around the whole of the inside of the feed pulley here. It only takes up a small portion of it. This has two effects. First of all, it reduces the cost of the overall unit because we're using less magnetic material. Also, this smaller pulley configuration allows us to run at higher RPMs, which gives us greater force, which for some applications is very good. So it has process advantages there. It also, because the magnetic field, the sphere of influence of the separator is really from here to about here. This is where the magnetic field is influenced, and we get eddy current separation. It means that this area here down the bottom is an area of low magnetic field, which means that we don't have so much of an issue of magnetic particles being attached here, wearing the belt out. So we have a better release zone for non-conductors in this area because we have a lower magnetic field. So it does have some process advantages. Some of the disadvantages of it are that because this is a narrower pulley structure, it means that the belt width, the effective width for practical manufacture is less for an eccentric eddy current than a concentric eddy current. Concentrics can be manufactured to wider belt widths, hence higher capacity units. So for some clients it makes much more sense to have a concentric unit because they need 2 meter wide belts, and you can't do that with an eccentric, simply because it's a narrower belt, narrow pulley system, which creates more flex, which means it's less stable, so you can't run at greater widths. There's a trade-off between width of pulley and flexing, as it were. Typically, the eccentric rotor takes up about 2/3 of the total diameter of the unit as a rule of thumb. So eccentric designs are great for some applications. Likewise, concentric designs are great for some as well. So this will contain, this is a concentric design where basically there is a very little distance. We want to keep the distance between the magnet here and the belt, surface of the belt, as small as possible. Hence we get a good projection of magnetic field onto the surface here, across here. However, we do, in the discharge zone of the rotor, you can see that we have a high magnetic field here. So if I have any nuts and bolts in my feed that are mild steel, they're going to stick on here, damage the belt. Any fine dust will build up over a period of time and start to build up on this point here, and can cause wear on the belt from the inside. So as a rule of thumb, concentric designs tend to be used for larger sized material, in particle sized material, and also for higher capacities, because we can make these types of design of rotor much wider without having any issues in flex of the rotor at 2000 RPM. So, eccentric configurations, we have, just to recap, we have the offset eccentric rotor. Also, a function of that design is it's easier to position this rotor closer to the outer coverage and also the belt, so we can actually get a reduced distance, which gives us a higher concentration of eddy current closer to the surface of the eddy current separator. So that makes them great for finer particle size materials in the region of, say, 5 millimeters to 3 millimeters. You would usually recommend an eccentric unit for that sort of configuration. As I said before, we can get higher rotor speed due to the smaller rotor diameter, gives us greater change of flux, and we have a low magnetic zone at the bottom of the unit, which allows discharge easily if we do have a stray magnetic particle getting in, or a paramagnetic particle getting in. Concentric rotors use all the rotor surface. We have a larger separating zone than an eccentric. We have a greater magnetic field projection because we have more magnets in the separating zone, and we can use bigger blocks of magnets. We can process a larger top size, which is important for some applications. We have a greater feed capacity, and also greater belt widths are available in this type of design. So if you look at the specifications for the eddy current types of design, Bunting make 4 basic types of eddy current separator: the high intensity concentric, HIC, high intensity eccentric, HIE. These are machines that have 24 poles in them, so you're getting a great rate of change of north to south in the separating field. As you can see, the magnetic rotor diameter in the concentrics is 300 millimeters. It's less in the eccentric. It's 190 millimeters, so about 2/3 of the total diameter. And you can see what effect that has on the maximum operational width of unit that can be produced. So we can go up to 2 meters in a concentric and about 1.25 meters in an eccentric type eddy current separator. So that's why, if a customer has a very high capacity application, often the concentric is a more sensible choice. We also make an R-type separator, which is really a hybrid between a simple can sorter and a more complex high intensity unit. And then we have the can sorter itself, which is used for basically easy separations, things like aluminium cans from household waste. And because these aluminium cans are very large in particle size, we don't need a lot of poles in the eddy current separator. We can get a good separation with using just 6 poles. We have a smaller diameter rotor, and we run it because these applications tend to be quite low capacity. We run at belt widths between 300 millimeters and 600 millimeters. So if a customer is looking for a cheap method of processing relatively low quantities of aluminium to recycle aluminium can material from household waste, materials like that, then the low cost efficient option would be the can sorter for those sorts of applications, because it's an easy separation and you don't need a high eddy current field and lots of poles to get a good separation of the aluminium can material. So it offers a good technical solution which will have a short payback period and low capital cost. And as I said, the R-type separator is a hybrid between the two, where we have more poles, 12 poles, and a slightly bigger rotor diameter. And we can go, in those sorts of separators, we can go up to, again, about 1.5 meters in width. And therefore, applications that are not so simple, but still don't require 24 poles and a complex design. So let's talk a bit about the high intensity units, the HIC and the HIE. These units, in the case of the HIC, the concentric unit, can be made up to 2 meters in width and handle very large throughputs. The technical features are, for the HIC, that we would have a 300 millimeter diameter rotor consisting of the highest grade neodymium boron magnets. The HIE, the eccentric version, will have a smaller diameter, 190 millimeters, Both have 24 poles, which allows for separation of very fine non-magnetic particles down to about 3 millimeters in size. Variable rotor and belt speed to control the degree of projection of a particle from the belt surface, as we talked before. A key issue is the difference in feed speed on the belt and the speed of the motor. That gives you as a key effect on the throw of the conductive material, and both of these are independently controllable on the control panel. They also have a quick belt change system using belt jacks and a cantilever system that you see here, which makes it easy, about 20 to 30 minutes to change the belt on one of these units should you have a problem. It's fair to say that if you're feeding the material correctly and you have very little ferrous material on your feed, then you shouldn't have a problem in the first place, really. So good housekeeping will often maintain the belt for a very long period of time. The can sorter is the basic design which is used for non-ferrous beverage cans from dry recyclable household materials. Low cost option because it's a simple application. And this is an example of a can sorter. And here we have an example of a overband magnet here, which will just remove any ferrous material before it goes onto the separating zone here. So if you don't have a lot of ferrous material, an alternative to a drum magnet beforehand is some sort of overband that will take material out and remove it, leaving only conductive and non-conductive and no ferrous material going into the separating zone. And here you have your conductors thrown this way and non-conductors thrown off by their centrifugal force, and a simple splitter plate position that will move the splitter plate in and out depending on the separation you're trying to achieve. So the can sorter is a simple, cost-effective design for applications. A 6-pole rotor which takes the cost out of the process. It often comes with a preset belt and rotor speed. Again, it's a simple application, so you don't need the complexity of adjusting the belt speed and the rotor speed by eye. Once it's up and running, it will run on your application and requires no control on it at all. For general household waste, Bunting have designed the Eddy Current Separator R-type, which fits in the range between the can sorter and the high intensity ECS range, and it contains the key elements of both design. It has higher throughput capacity than the can sorter. We can go up to belt widths in the region of 1.25 meters. It has a 12-pole rotor, so consequently you have more magnetic hits than a 6-pole, which will allow it to separate out smaller particle size. And normally this will come with a variable rotor and belt speed control, because the applications are slightly more challenging than the can sorter applications. The final option we can offer is a mobile eddy current system, which is mounted on Caterpillar tracks and comes basically ready to run on site and move around a site if you are on a reclamation site, for example, and moving around clearing the ground clearance and recovering material from it. So our mobile eddy current will come with vibro feeder, a rare earth drum for fine ferrous recovery, which you tend to get a lot on these landfill sites, 1.5 meter wide high intensity eddy current separator, discharge conveyors with hydraulic folding for transportation, hydraulic power packs for the crawler unit, a 65 kilowatt generator, but it can also be run by mains should that be available, adjustable rotor and conveyor speed like a high intensity eddy current separator, onboard air compressor and onboard walking light. So it comes as a complete package. We'll now talk a bit about the technical background of eddy current separation. It's basically the principle of putting a conducting particle in a rotating magnetic field that is changing polarity. So in accordance with Faraday's law of induction, electrical currents are induced in a conductor that's entering a rotating magnetic field. By Lenz's law, the induced eddy currents created in that magnetic field oppose the magnetic field that's been created. So our changing magnet in our eddy current pulley is now reacting with the magnetic field generated in our conductor, and that results in the conductor being repelled away and thrown off from the pulley in quite a violent way in sort of applications where you have high conducting material. So you get a really pronounced throw of material by a combination of Faraday's law and Lenz's law. Now, what defines how far something is thrown is, first of all, the conductivity density ratio of something. The higher that is under normal circumstances, the further it will be thrown. So as you can see from this table here, aluminium is the most responsive and easiest to separate out on a eddy current separator. Copper is next, and then we have material that has a less vigorous response, material like zinc and brass and tin. Material that has no response whatsoever are materials that are non-conductors, and here you're looking at stone, plastic, glass, all the sorts of materials that you get in recycled applications. So you should be easily able to separate out highly conductive materials from non-conductors via Faraday's law and Lenz's law. So the design variables that sort of influence how we design an eddy current separator, we'll talk a bit about that. The first design variable is rotor speed. The number of changes of north and south pole as a conductor passes through the area of separation of the eddy current will determine the throw of the machine. The more changes from north to south, the greater the force, and the more likely you are to capture a smaller particle. So different manufacturers have different rates of rotor speed, typically between about 2,500 and 5,000 RPM if you looked at the different manufacturers' specifications. However, there are also other factors to consider, such as the higher the RPM, the greater the maintenance and wear on the bearings, etc. So as rotor speed increases, the design stress on the machine increases, so there's always a trade-off. So if you look at the distance of throw, for example, of a constant particle of the same size from an eddy current, you can see up to a certain point we get value for money for our increase in speed and increase in cost of manufacture. But after you reach about 2,500, then you're beginning to get very little increase in throw and increase in separation performance. So this is why sort of standard eddy current separators tend to operate in the 2,000 to 3,000 RPM range, because that's where you're beginning to get towards the top end of the effective speed, which can influence the distance of throw, and it's also working in a comfortable mechanical area for the eddy current separator. Going up to 5,000, as you can see in the case of this particle, is going to have no effect on the throw whatsoever. So it's really an extra cost to the client if we manufactured at those speeds. Okay, the next design variable is the feed method that we applied to the eddy current separator. As with all physical separation devices, it's essential to have an even monolayer of settled material going into the separation zone of the physical separator, in this case the eddy current pulley at the front. So consequently, this is one of the reasons why we have a long belt feed, and these machines tend to be have a long belt that allows these ballistic particles, often of quite large material, to feed and be settled before we get into that separating zone. In an ideal world, you'll feed via a conveyor system which allows an even width of material across the whole of the front pulley of the separator as well, which increases your capacity as well. Here we have the feed system for a eddy current separator. So we would feed onto the vibro feeder here, which will feed onto our magnetic drum separator located here. Our magnetics from the drum separator will be discharged here. This might be a ferrite separator, which is low intensity. If we have our contamination is large nuts and bolts and tramp iron, mild steel. It might be a rare earth drum if we have finer particle size and some material that's not liberated that has a medium magnetic susceptibility. So we have our drum magnet here. The discharge from the drum goes onto our belt, and our belt will feed into the separating zone of our eddy current unit here, where we'll separate out our conductors and our non-conducting units. So again, you can see there's quite a long distance between here and the separating zone. That is to allow the material to come settled and present itself in the best possible way to the operating pulley of the eddy separator. Other options you can get on eddy current separators are sequence control panels, which allow, as I said before, allow you to control both the belt speed, the vibratory speed that you're feeding on as well, and also completely control the speed of the eddy current rotor, which again is one of the key control variables on the machine. We can have our drum magnets to remove ferrous material. If we have very little ferrous material and it's quite large in nature, you can go to an overband magnet, which is a simpler design. We can have modular design, as we've seen. We can even mount them on Caterpillar tracks. You can have rotary or static belt cleaning to, if you've got a slightly damp material or material that's quite has quite a lot of adhesive particles there, to clean the belt before it at the bottom before it goes back to underneath the vibratory feeder. And for high wear applications, you can have a ceramic coating on the non-magnetic ceramic shell, which creates an armoured surface which will allow longer life for the machine in hostile environments. So some ideas of capacity for these machines for different applications. So really you can run up to about 20 tons per hour per metre width of unit for materials like aluminium dross, which is reasonably high density, household refuse. I think smaller units, smaller applications would be things like plastic waste, which is granulated. There, because it's a lower density material and finer in particle size, then you would really be looking at 2 to 3 tons per hour per metre width of unit. And a different type of unit specified. You see, for the finer particle size ranges, we're specifying the eccentric unit. For the larger particle size range in 440 millimetres, we're specifying the concentric unit. So there's not a best type of eddy current separator. There is the best type of eddy current separator for the client's specific application. And what we would do in our test centre is test them on different units and come up with a flow sheet that would optimise the separation for the client and also optimise the cost benefit that they will get from the process. So I think we're now going to move to some videos of machines in operation, and the first one is processing light industrial waste. This is our laboratory in Redditch, eddy current separator here. Phil Tree is putting material over the rare earth drum that you see there, and that's the magnetic fraction from the rare earth drum. It's gone over the front pulley. There you see the pulley splitter plate position here. This is the non-conductors, and this is the conductors here. That's the non-conductors, which is shredded waste, and here you'll see the conducting material, which is a lot of stainless, a lot of aluminium there as well. So that's one of the units we use in our test facility. This is an example, this is a research and development example where we are running the eddy current separator, and we're processing shredded lithium-ion battery material. Here we have plastic from the shell, the lithium-ion car battery, which is used to as a electrolyte barrier and used for containment of the electrolyte. And we have anode and cathodic material, which is aluminium and copper, they are often coated in other oxide layers, so they don't look like aluminium and copper in this particular application. So we have a mixture of plastic, and a mixture of the black material tends to be coated copper with graphite materials like that. And again, we have our splitter plate set up for a separation. As you see, material being thrown from the unit, and mainly our plastic going around unaffected. So here, what I'm doing is creating here a concentrate of aluminium and copper cathodic and anodic material, and removing the plastic material for recycling. That anodic and cathodic material would then go for magnetic separation to separate out the anode from the cathode, and then go for downstream processing accordingly. That's an interesting application that's beginning to be seen for these sorts of new applications that are going to become quite common as electric vehicles penetrate the market more for domestic transport, and also they become older and have to be recycled. So this machine itself is actually designed for that particular application. Okay, another application here is wood-metal mixture. This is building material that's gone through recycling. So this is a much more coarser application. You see the particle size is much larger, and we're feeding in a mixture of wood, aluminium and some ferrous material through the processor. See very large lumps of material. And here we're going over our drum separator to begin with. Ferrous is removed, and we're now moving into the separating zone of the eddy current separator, and you can see that the nature of the ballistic throw of the aluminium is very pronounced, and our wood is going over and separating the other side of the splitter plate. So I can see it's quite a forceful separation of the larger aluminium particles from the process. So just to summarize, we design our eddy current separators to provide the optimal eddy current field for your particular application. They separate small particles of non-ferrous material from other materials down to about 3 millimeters in size as a rule of thumb. The low maintenance conveyor is made of extremely tough urethane belts to allow longer wear, and also the cantilever change system means that should you have a problem, then you can change a belt very quickly indeed. We have inverters to allow optimizing belt speed very easily and control that very easily, which allows for operator control on site. We have a range of different eddy current rotors to choose from depending on your material specification and your budget. And we can also custom design combinations of different units, including drum magnetic feeds, high intensity magnetic separators prior to the machine, cross belt separators and vibratory feeder trays, and even do modular designs of mobile units as well. So that concludes the talk. The question you may have after watching this: what do I do if I have conductive material below 2 to 3 millimeters in size? Well, the answer to that really is an eddy current separator's performance will drop off below that particle size range. And the machine to consider for those sorts of applications would be an electrostatic separator, whose operational area and operational particle size for removing conductive from non-conductive particles is between 4 millimeters down to about 100 microns in size. So they work perfectly well below 2 millimeters in size and will separate out copper from plastic, aluminium from plastic materials and glass and things. They are something to consider if you have a very fine waste stream from your process plant that you are not doing anything with at the moment. So that concludes my talk. Hopefully it's been of interest to you, and thank you for listening.